All right, let's get right into it. Today, we're doing a full technical debrief on the Trivy supply chain compromise. We're going to break down exactly how a group called TeamPCP managed to turn one of the most trusted security scanners into a powerful credential stealer, operating right inside our CI/CD pipelines. To really grasp the scale of this, just look at this number: 76 out of 77. In one single coordinated move, the attackers compromised pretty much every single release tag of the trivia action. Think about that. Almost every version that teams thought they were safely pinned to was actually poisoned. And that, of course, brings us to the incredible irony of this whole incident. The very tool that thousands of teams depend on to find vulnerabilities and lower their risk, well, it became the weapon. And the scariest part? The malicious code ran silently, before the real scanner ever did. This meant all the CI/CD pipelines just kept passing, showing green check marks, giving absolutely no sign that secrets were being siphoned off in the background. So what exactly went down? Let's dig into the components that were hit and the timeline of the attack. This wasn't just a simple single-point failure. The attack was comprehensive. They hit the main GitHub action, they hit the setup script that installs Trivy, and they even backdoored a specific binary release. This was a deep compromise across the project's entire delivery chain. Now, how fast did this happen? The whole attack unfolded over a really critical 12-hour window. On March 19th, the attackers got in, and within about an hour, they had repointed dozens of version tags. It wasn't until the next morning that things were restored. That means any pipeline that ran this action during that window was completely exposed. And this is the key takeaway here: the stealth. The malicious code was just prepended to the legitimate script, so after it was done stealing credentials, it just kicked off the real Trivy scanner. To any developer, to any CI/CD system, everything looked perfectly fine. You got green check marks all the way down, while your secrets were just flying out the back door. Okay, so that's what happened. Now, for the big question, how was this even possible? Well, it all comes down to a really fundamental and often misunderstood feature of Git called mutable tags. So, quick refresher for everyone. A Git tag, something like v0.34.2, it isn't the code itself. It's really just a friendly little label, a human-readable pointer that points to a very specific, unique commit, which we call a commit SHA. Think of it like a shortcut on your desktop. It just points somewhere else. And this slide right here gets to the absolute heart of this attack. A commit SHA is immutable. It's a permanent cryptographic fingerprint of the code at that exact moment in time. You can't change it ever. But a tag? A tag is just a pointer, and that pointer can be moved. It's convenient for us humans, for sure, but it gives you zero guarantee of integrity. And this visual shows you exactly how they did it. The attackers, once they had write access, just used a force push command. They took that tag, let's say v0.34.2, and it just moved it from the original legitimate commit over to their new malicious one. They even went so far as to spoof the commit metadata, the author, the date, to make it look completely identical at a quick glance. So the lesson here is pretty stark, right? If your CI/CD pipeline trusts a version tag, you are trusting a pointer that can be moved. And if an attacker gets write access to that repo, they can silently redirect that pointer to their own malicious code, and your build system will just run it. No questions asked. Okay, so the attackers found a way to get their code into the pipeline. But what did that code actually do? Let's pull apart the payload. Now, this is where it gets really clever. The malware wasn't a one-size-fits-all script. It actually adapted its strategy depending on the environment it was in. So first, let's look at what it did on a standard GitHub-hosted runner. On these runners, the payload was incredibly precise. It decoded a Python script and ran it with sudo, which is just available by default. This script then went hunting for the runner.worker process, the very thing that handles job execution. From there, it read the raw process memory, scraping it for a very specific JSON pattern that GitHub uses to mark secrets internally. It was a surgical strike, designed to pull credentials right out of active memory. But what about self-hosted runners? Well, those environments can be totally different, much more diverse. So here, the malware switched to a much broader, more aggressive strategy. So instead of that precise memory scraping, it just went for a massive sweep of the entire file system. And look at this list of targets. It's exhaustive. We're talking SSH keys, credentials for all the major clouds, Kubernetes tokens, Docker configs, Terraform state files, which often have secrets just sitting in plain text, and it even looked for cryptocurrency wallets. It was a total digital smash and grab, just looking for anything valuable. So the key here is that this wasn't some clumsy script. This was an adaptive, intelligent payload. It understood the difference between a standardized, temporary GitHub environment and a potentially permanent, target-rich, self-hosted runner, and it tailored its attack to steal as much as it possibly could from each. But the attack didn't stop with just stealing CI/CD secrets. Nope, that was just phase one. What the attackers did next really shows the cascading danger of these supply chain attacks. This timeline shows just how quickly things escalated. Less than a day after the Trivy compromise, the attackers were already using stolen NPM publishing tokens to launch a second supply chain attack. They started pushing malicious packages to the NPM registry, a whole campaign they called Canisterworm, which ballooned to over 100 packages in no time. And this is such a critical lesson in modern software security. Our supply chains are all connected. A breach in your CI/CD system doesn't just put your secrets at risk, it can literally hand an attacker the keys to compromise totally different ecosystems, like package registries. It turns one incident into many. So why does this stuff keep happening? This attack wasn't based on some exotic, complex zero-day. No, it exploited systemic problems and just plain flawed assumptions that are baked into a lot of CI/CD security models. The thing is, we've built our pipelines on a foundation of trust that's often just misplaced. We trust mutable tags because they're convenient. We focus all our security energy on scanning for CVEs in our code, but we forget to check the integrity of the tools we're using to do the scanning. We grant super broad secrets to tools that might only need to read a single file. And maybe worst of all, we tend to give security tools, like scanners, a higher level of implicit trust, which creates this massive, dangerous blind spot. Okay, that's enough about the problem. Let's talk about the solution. What can you and what should you be doing right now to harden your own pipelines against this exact type of attack? Here is your remediation campaign. Number 1, and this is the most important, pin your GitHub actions to their full immutable commit SHAs, not tags. Number 2, if you were exposed, you have to rotate every single secret that was accessible to those workflows. Assume they're compromised. Number 3, audit your runners and your logs for indicators of compromise, especially any network calls to the attacker's typo-squatted domain. And finally, number 4, do a thorough review of dangerous workflow triggers like pull_request_target and make sure you're not giving away secrets to pull requests from forks. And this right here perfectly illustrates the single most effective change you can make. On the left, that's the vulnerable pattern, referencing a tag that can be moved. On the right is the secure pattern, referencing the full unchangeable commit SHA. This simple change moves your pipeline's trust from a flimsy pointer to a solid cryptographic guarantee. Let's just end with this. The Trivy compromise wasn't just an attack on one tool. It was really a stress test of the entire CI/CD security model that so many of us rely on. And the results are in. If your security scanner can be silently turned into a credential stealer, your trust model is fundamentally broken.